going to talk to you about networking research, okay, and this is the outline of my talk. First, I'm going to talk to you about what networking is and is not, okay? I'll get to that in a moment. I'll talk about some publication trends, some fundamental problems, and then three current important areas of research that are complementary, but also they're very related to each other. Okay, so how many of you have taken a networking course here at KAU? A few of you, okay? So have you, when you went into the networking course, okay, did you learn many TLAs and FLAs? You know what a TLA or FLA is? TLA is a 3-letter acronym, FLA is a 4-letter acronym. Did you learn a lot of acronyms in that class? I bet you did. So most of my students, when I go, when I teach networking, right, most of the students, this is what they seem to get out of networking. Lots of TLAs and FLAs, okay? A heap of header formats, bunch of boxes, a ton of tools. So let me just give you some examples of that. So, you learn about BGP, OSPF, TCP, UDP. There's actually one acronym that it's only a 2-letter acronym, IP, and this is the king of protocols. It's just like, some of the rock stars that go only by one name, like Beyoncé, for example, right? And so IP doesn't need 3 letters. It's a very important protocol. It can only do with 2 letters, all right? Someone told me, a colleague of mine, when I was doing my PhD, he said, I took this networking course and I went to sleep when the IP header format was on the board and at the beginning of the semester, and I woke up at the end of the semester when the TCP header format was on the board, right? So yeah, we get we teach a lot of header formats. You learn about a lot of boxes, okay? Routers, switches, bridges, NATs, firewalls, accelerators, sniffers, proxies, load balancers, right? And you learn a lot about tools, all right? The best one I like is Snort down here, okay? So, so there's a lot of things that many people associate with networking, right? But I want to think that this is not what networking really is about, okay? I'll tell you why networking is actually very cool. I don't know if you can see the header at the top, right? But I believe that networking is really cool, and here's the reasons why I think it is cool. It is tangible. How many of you do not have a smartphone? No, none, right? So the next time that someone comes up with an acceleration protocol that gives you, really blazing speeds, will that affect your life? I bet it will, okay? How many of you are not going to click on a link on a browser today? Everyone will, right? Networking is tangible. We actually make use of that every day, multiple times a day, and in fact, this is the important thing, okay? We don't even notice that we are making use of that. You know what the best technologies are? The best technologies are those that disappear. You use them and you don't even think about them when they're there, right? Like electricity. Do you think where electricity comes from? No, you just plug in. The same with networking. You click on the link, you know what happens? No. Why? Because it's a very important technology, it touches our lives, and it has disappeared in the background, okay? It's inherent, important to almost every important problem. You know what happened? Lots of theory people back in the day, they used to prove things about approximation algorithms and NP-hard problems and polynomial time schemes and all that, okay? When the internet came along, you know what happened? They jumped into networking. A classical example is Christos Papadimitriou, the famous theoretician who's been doing the last 10, 15 years, has been doing research in areas that relate to networking, okay? most important problems in our lifetime right now is basically related to networking. It is inherently interdisciplinary, okay? I'll get to that in the next slide, but if you want to establish collaborations with colleagues, working on network problems, network-related problems is the best way to do that, okay? It is a young field. It is a young field, which means it affords exercising problem selection and taste. When I say young, it's about 40 years old, okay? Compare that to mathematics or physics, right? Which means many of the important problems have not been actually addressed yet. Not only that, because it is a young field, you can make a huge difference by actually following your heart, your interests. So think about physics. A few years ago, unless you were doing string theory as a physicist, you probably couldn't publish your work. Why? Because there's these subfields, and unless you are in one of those subfields, you know, you're basically, no one is gonna regard you as doing important work. Not so in networks, okay? You have the chance to actually define what the new products and services are going to be in the future, okay? It provides platforms for building your ideas. There's a lot of tools, and there's a lot of tools out there. So if you really want to start something, you don't have to start from scratch. You can actually use all these open source tools and build from there, okay? And it includes widely read papers. I'm gonna get to that also in a couple of slides, all right? So, interdisciplinary research. It is truly interdisciplinary. I don't know of any other field that has such broad connections with other fields, okay? In my talk yesterday, I talked about algorithms, I talked about graph theory, I talked about optimization theory, but that did not even scratch the surface of of the kind of research you can do with networking, right? You know, all these fields, one way or another, are related to networking, okay? So if you're doing research in the broad area of networking, you can actually touch upon many other disciplines. Okay, now I'm going to talk a little bit about research publication trends, just to show you how important the field has been in the last 20 years. In fact, this information comes from a paper that was published in the Communications of ACM in October of last year. So it's a very recent paper, and what they did is they looked at publication trends over the last 20 years in ACM and IEEE, okay, which are the two main publishers for computer science-related work, okay? So here's the interesting thing. So this graph shows for 20 years, starting 1990 all the way to 2010, the number of publications every year. And they have broken down by color, okay? And look at the blue one. Can you read what it says here? Computer networking. So you can see the importance of the field has increased over the years. This is number of publications. Look at the fraction of publications, right? So about more than 10% of all publications today that come from networking. If you are not doing research in networking, you are missing these trends, right? And, you know, so for example, artificial intelligence is very important. Data management, you can see how it became important in the last few years. And let me see, human-computer interaction used to be, you know, very popular, not so much today, okay? That's from ACM. Let's see what IEEE does, because most networking papers actually appear in IEEE publications. So look at this, same color coding, okay? This is networking. Look how much the field has grown from 20 years ago. As a fraction of publications, it's almost 40% of the total today. There's a reason why people do research networking. It's tangible, right? It's relevant, it affects your lives, and you can see the results immediately. That's why they do it, okay? Now, let's look at trends in IEEE. So it shows you the top 20 trends, you know, trends that are going up, and the bottom 20 trends that have been going down in terms of publications over the last 20 years. look at the top 20 ones. Internet, sensor network, wireless, network, data transmission. 5 of the 20 uptrends over the last 20 years are in the broad area of networking. Okay? If you're not doing research in networking, you've missed this wave. All right? And it's not going to get, it's actually going to get better, not worse. Okay? Networking touches all our lives. So, I'm going to talk to you a bit about fundamental problems in networking. And these are fundamental problems that used to be research problems, research challenging some time ago, and there have been very good solutions as a result of those research challenges. Okay? But the reason I'm going to talk to you about problems is because you are computer scientists, right? And what do computer scientists do? Solve problems. Were you here yesterday? No? Okay. So they solve problems, okay? That's what we do as computer scientists. We don't do programming. We don't just play around with codes. We don't do buffer management. We don't just write protocols. We do all of these things, but the reason we do all these things, these are tools to solve real problems, okay? And so let's take a look at, the last 20, 30 years, the kind of problems that came up in terms of doing networking and see some of the solutions. So, fundamental problem. Originally, you just had your computer, right? Today, if you just have your computer without internet connection, there's nothing you can do, and pretty much impossible to do anything, right? I mean, you can play games maybe, right? But you can communicate, which is the essence of using the computer. So you had to physically connect devices, and so people came up with many, many, many solutions: encoding, framing, error detection, reliable transmission with window or sliding window protocols, multiple access protocols like Ethernet, wireless protocols, and so on, okay? These were, at one time, research challenges that have been solved. Does that mean that there are no problems in the future? Absolutely there are, okay? There's a huge new area in terms of smart grids, okay? Energy efficiency. You can use very smart algorithms to control the efficiency of various devices, and you can do that by using specially designed network protocols, okay? These are just examples, okay? There's many other open areas, of course. Here's another problem. Not all the devices are directly connected, okay? Which means you have to have introduced switches, routers, you have to have protocols like IP, global addresses, things like ARP and DHCP. DHCP, you use DHCP every time that you connect to a wireless network. You don't know it, okay? It's automatically done for you in the background. Routing, switch fabrics, things like that, okay? Does that mean that there is nothing to do in the future? Absolutely not. Future internet, and I'm going to talk a little bit about it when I talk about network architecture in a moment. Next. Scaling to billions, right? IP came along. There was a handful of universities back in the 70s. Today, you have billions of people connected to the internet. In fact, probably you have more machines connected to the internet than people right now, okay? So what are the problems there? Well, you can't do routing in a flat network, so you have to break it up into routing areas. Then you have to have new protocols like BGP. You have to have more addresses like IPv6. You have to be able to do multicasting efficiently, and so on and so forth, okay? Now, what is the next problem? Scaling to billions was one thing. How about scaling to trillions, right? Internet of Things. Everything is a smart device that's connected to the internet all the time, okay? What kind of new protocols, algorithms, methods you need to control this, okay, to efficiently route among all those devices? Devices can be disconnected and come back, right? And so there's a lot of challenging problems that are associated with all this, with having trillions of devices connected, right? Another problem, So we solve the connectivity. Now you have to get processes to communicate. So you have protocols like UDP, TCP, remote procedure call, transport for real-time applications, the real-time protocol, and so on. Okay? So what's next? What happens when you have all these transport protocols? You have a lot of diversity, okay? That makes the internet heterogeneous. But look what actually has happened. Let me ask you this. Have you streamed a movie or a song over the internet? What kind of protocols do you use when you do the streaming? I'm sorry? HTTP. And HTTP runs on top of TCP. So here's the interesting thing. You have another protocol for transporting real-time applications, yet pretty much every real-time application uses HTTP for transport, which means you are actually using TCP. So although TCP was thought that, you know, if you get to real-time video, audio, and all that, you may actually get most of the traffic out of TCP, the reverse happened. You know, 90 to 95% of the traffic in the internet, in fact, runs over TCP. Is this the best solution? Who knows, okay? There's a lot of research that needs to be done to determine that. Another problem, allocating resources, okay? So now you have queuing disciplines. You have to do congestion control, okay? There's lots of variants of TCP to do congestion control. Congestion avoidance, like random early drop. Quality of service, things like RSVP, IntServ, DiffServ, and so on, okay? What happens now? What happens now is that the traffic patterns become very, very dynamic, and doing any of these things are actually much more difficult than it used to be. So think about the data center networks, okay? Once you do an update on your Facebook account, what happens? You know what happens? All you've done is you posted something on your Facebook account, but what has happened is this has resulted in thousands of connections between different machines within the same data center and across data centers. Why? Because they have to actually go and update the indexes for your friends and your friends' friends, and so on and so forth. So the traffic patterns have become completely dynamic, okay? And so doing all of this, allocating resources becomes even more difficult, right? What about the data? Okay, I was able to take data from one place to another. What am I gonna do with that, okay? I have to somehow present it to the user. So now you have all these other protocols or algorithms that do the presentation, as you can see here, okay? What is the next problem? The next problem is video. Video is already more than 50% of the traffic, okay? We use it more and more every day. So what happens in a world where 90% of the traffic is video? I don't know. We need research to find out, okay? Then you have applications themselves need their own protocol. So you have, you know, traditional applications like mail, HTTP, and so on. Session call control for multimedia like SIP, SDP, and so on. DNS, SNP, you know, for infrastructure services, management, and directory services. And then you have all these new applications like overlay networks, all right? All of these were challenging problems. They were solved. Emerging challenge, network virtualization. I'm going to talk about that later on. And then finally, security attacks, right? So someone has to protect the users from these attacks. So now you have all sorts of really interesting interdisciplinary research, okay, that comes together to deliver solutions, robust solutions for security. And then what's the next step? Well, the next step is there's huge number of challenges in security, all right? Imagine if someone were able to get on your smartphone, right? That's gonna ruin your life. Well, is it gonna ruin your life if it gets them in their smartphone, or if they get in your smart home? because now many devices in your home are going to be controlled by the internet, okay? I actually have an application here which allows me to turn the lights on or off in my house, okay? So what if someone gets access to that one? Right? So lots of interesting challenges here. All right, so that's the whole point, is that there have been a lot of fundamental problems networking. There's a lot of more challenges that are coming up. Okay, so what I'm going to do is just go over 3 research areas: network architecture, network virtualization, and software-defined networking, and just kind of explain some of the research trends that are going on right now. Okay. By the way, if you have any questions, feel free to let me know. Okay. All right. So, if you look at the current internet architecture, I told you there's a lot of FLAs and TLAs, right? So typically, what you have is this hourglass structure. Okay, and IP is in the middle, and the idea is that everything runs over IP, and IP runs over everything. Okay. And so this is the narrow waist, this is the convergence point, okay? And so as long as you have IP, you can be pretty sure that any protocol will run on top of it, and then any transport technology is going to run under it, okay? But does that mean that this has solved all the problems? The answer is actually no, okay? Here's why. When this was developed, the internet was an academic curiosity, okay? Now it's a commercial platform. Very different requirements between the two. Let me point to some of them. It was trusted academicians that exchange emails with each other, right? Now you basically have connections between untrusted systems. It was a research network. If it went down for a day, you know, some professor might complain that they can't get you the work done. Okay? What happens if your internet connection goes down for 15 minutes? There's going to be in the news, right? If you look at mobility, this was when the internet was designed, identity and location was the same thing. Okay? You have an IP address that identifies the machine and where that machine is. Okay? Is that true today? Absolutely not. Okay? You can cruise down the highway or along the Jeddah highways, and you can get your internet connections going, right, all the time. So mobile IP has helped with that, but there are more challenges. Imagine when every vehicle is equipped with one of these devices, IP, okay. Performance, so it was best effort delivery and stateless. Did not keep any information inside the network. Today, we want quality of service guarantees. Do you really want your network connection to go down when you're watching your favorite football game? Not really, right? So, communication model, it was host to host, okay? IP address to IP address. Now it's a globally distributed system. When you make that Facebook update, do you know where that update is being made? You have no idea. Facebook somehow routes it to the nearest maybe data center. Within that data center, it may have 20,000 servers, okay? Which one is handling your update? Who knows, right? Is it the same thing? No, it's completely different requirements now, right? If you look at delivery model, IP networks are designed for one thing only. Take that packet and send it out as fast as possible, okay? So you have a lot of research and development in these packet switching architectures that are optimized to do exactly that. Today, that may not be as important. What you really care is content, right? And so that's maybe more important than just very fast forwarding. Connectivity, when the internet was designed, it was between persistent end systems, right? You had a machine in your lab, and you communicated with another machine in another lab, okay? Not today. Your smartphones get in and out of connectivity all the time, and the architecture has to be able to accommodate that. Okay. The focus goes machine to machine. Not today, it's human to human, right? So there's a lot of other things that one has to consider when looking at the network architecture. And so what typically has happened is that the internet has been patched to kind of take all those into consideration. So what we have, what the result is today is basically a patchwork of fixes to accommodate some of these new requirements. So the question is there a better way to get around that? And so here's, if you look, for example, at content distribution networks, right? The narrow waist will not be at the IP layer anymore. It could be much higher. It will be around contents, okay? And so this is a very different strategy, as you can see here, than what you have over there. Now, there have been a lot of work in the last maybe 7 or 8 years on what is called the clean slate design. Okay, a clean slate design basically means that you design a network from scratch. Okay? So don't be constrained by the underlying system as we have it today. Use the experience that you have gotten, doing research over 20, 30 years in the internet, so as to design a new architecture that has a fresh look at the problem space, okay? Now, this takes a holistic approach to redesign the architecture, and you also need what is called experimentation at scale. How would you know that whatever you design actually is going to work? Okay? You can't know that unless you experiment at the scale of the internet, okay? And you also have to be able to accommodate future changes. So there's a lot of work going on throughout the world on future internet architectures. Okay, I'm not going to talk about all the possible or all the possible research that is out there. I'm only going to just give you a brief introduction to some of the future internet architecture projects that are going on in the US right now. Okay, and so there's basically 4 projects that are in the order of about $10 million each that are looking at various architectures. One is the named data networking that is led by UCLA, and the focus here is on the what, not where. So in other words, you don't say, I want to get the content from the CNN server, you just say, I want to get this video, right? And the architecture will find out where that video is stored, and so you will have to have things like unique identifiers for the contents, and express that into the architecture, and the architecture will take care of that. Okay. There's another project that is called the Mobility First project, and that has a very different focus. Yes? So that's a very good observation. So it's similar to BitTorrent, but you have to keep in mind, so BitTorrent is an overlay network, right? And so it was designed on top of the existing IP architecture. This takes a very different view, which is, IP does not exist. I'm bringing the new architecture, right? And so it is similar in concept in that, again, you just name the content that you want to get, and the system will get it to you, but the way that it gets it from you is very different from the way that BitTorrent operates, okay? And, it will take me a while to explain exactly how it does that, but we can discuss that offline if you wish, okay? Now, there's another project that is led by Rutgers called Mobility First, and as you can see, the focus of that one is very different. It basically tries to see what internet architecture would scale to many, many devices, including vehicles that are interconnected. Okay. Nebula from UPenn, okay, it's yet a different system. This assumes that the network is the computer, which it is. So all the computation takes place inside the data centers, right? And so the idea is to develop an architecture where you have a high-speed core that interconnects data centers. And then it also allows mobile users to access those data centers efficiently. And then finally, this is the expressive internet architecture, which uses a very rich communication entities and uses security. Actually, all of these architectures have security in their core design, okay? Unlike the current internet, in which security was actually put in as enhancements to the protocols, these are designed with security considerations from the beginning. So as you can see here, here's the interesting thing, and that actually ties in with the network virtualization idea that I'm going to talk to you in a moment. If you look at each of these projects, right, they look at the architecture from a very different point of view, okay? And that is important because, first of all, if you are talking about clean slate, it's impossible to deploy, right? You can't just in one day rip out the existing routers and build in the new devices that will be needed for this architecture, devices, hardware and software, right? And so it is very difficult to define what is called the one-size-fits-all architecture, okay? It depends on the focus. If your focus is data centers, well, Nebula is a very good architecture, but if your focus is content delivery, where NDN is the best architecture for that. So how do we put all this together, okay? And so one way that we can do that is by network virtualization. And so instead of having a one-size-fits-all architecture, what we can have is all sizes fit into one solution, okay? It's basically a network virtualization is an open and expandable model that allows multiple heterogeneous architectures to coexist and share the underlying resources, okay? So what I'm going to do is just give you a very brief introduction to virtualization and then give you kind of a, because virtualization has been around for a long time, okay? Going back to virtual memory, okay? And so you started with virtual memory, then you had virtual machines at the OS layer, okay? Then you had virtual storage. Finally, you have virtual data centers in the computing, right? And so what's the next step? Well, it's virtual networking. So there have been, so the idea is the following, right? So you have a physical network, and what you do is you give different logical views to different users of the network, exactly like what a virtual machine does, okay? Now, there have been some instances of virtualization for the last 10, 15 years in the network space. And these, I'm gonna talk about this in a moment, okay? But these are just very special cases of what virtualization is considered to be today, and I'm gonna get to that. So if you look at virtual LANs, right, this is based on the idea of frame coloring, and so you take a LAN and you partition it into broadcast domains using the VLAN ID, right? And now you have completely separated the same broadcast LAN into multiple ones. So you have virtualized it. Okay. Another idea is the virtual service network. Okay. And you do that already here in KAU. When I turn on my smartphone, I see, you know, there's an access network for KAU students and faculty. There's one for guests and so on, right? So this is exactly the idea. Well, you can have a guests network that is limited in what the guests can do. There's the employees network, okay, which obviously you can do more things. And then there's the administrators network who have access and they can change configurations and all that normal users do not do. Okay, so that's another instance of virtualization. You can take that one step further. So what if you have an organization that is connected over the internet in multiple sites, has multiple sites connected over the internet, then you can have, you can connect these sites with tunnels over the internet itself, creating a VPN, okay, a virtual private network. And so you can have multiple layer 3, layer 2, layer 1 technologies that can achieve that. So it's basically you take that virtual service network, you extend it over the internet. And then finally, during the decade of the 2000s, okay, there was a lot of work on overlay networks, and the idea there was that there's a lot of services that require the network itself to be aware of context. Okay? Unfortunately, IP routers do not store any state, so they cannot be made aware of context. And so what you are basically doing, you're taking the physical network and you install at the application layer certain code, certain software that is aware of that context, and so you can do things like multicasting at the application layer, okay? You can do a lot of things that you can do with the internet itself. The problem with that is, of course, that this is very application specific. So you can have software like BitTorrent to distribute files, okay? But that's the only thing that it can do. If you wanted to do multicast, you can't. You have to install another piece of software that does application layer multicast, and so on and so forth. So this is application specific. So how can you generalize that? So I'm going to show you the model that generalizes this concept and gives you the idea of a very, very broad reference model for virtual networking. And this looks like this. At the bottom layer, you have infrastructure providers, okay? Then at the middle layer over here, you have the service providers, which create and manage the virtual networks, and they do that by leasing resources from the infrastructure providers. All right. Then you have users who select services that are offered by these service providers. And finally, you have brokers that will take these services, maybe put them together, compose them, and offer more sophisticated services to users. Now, you may think that this is kind of complicated, but this is exactly the way that air travel works. Okay, think about it this way. Who are the infrastructure providers in the airline model? It's the airports, right? And who are the service providers? The airlines. What do the airlines do? The airlines will lease gates from multiple infrastructure providers, multiple airports, and what they're going to do is they're going to offer you a service. So if you're going to go from Jeddah to New York, you have multiple choices of how to do that. You can get, fly on Saudi Airlines directly, or you can get a flight that stops somewhere in Europe, and so on and so forth, okay? And then you are the users, and you as a user, you can actually go to the airline directly and buy your flight, right, your ticket. Or you can go to a broker, which is basically a travel agent, and the travel agent has the ability to maybe look at multiple, the travel agent may be a physical person, or it could be something like Expedia or Travelocity, right? Who basically look at all the airline schedules, and they come up with a list for you, and then you can choose in terms of how long it's going to take or how much it costs and things like that, right? So this is not new. I mean, this concept is not new, has been very successful in other areas, but it's very new in networking, okay? And then you can do things like this. You have one infrastructure provider and another infrastructure provider, and then you have the service provider 1 and service provider 2, and the service provider will basically, just take resources. You tell it, look, I have offices in these 3 cities, build me a private network that serves these 3 cities, right? So it will just lease the appropriate resources from the infrastructure provider, give them to you, okay? Then you may sublease those, so you may act actually as a service provider as well, and sublease some of those resources back to another, another user. And so you can actually, as you can see here, you can have multiple virtual networks that operate with each other. And so there's an interesting things that you can do. So you have concurrency, multiple service providers. You have nesting, where you have child virtual networks that are derived from parent virtual networks. You have inheritance, which is very similar to the object-oriented language idea of inheritance, okay, and so on. Right? So you have all these really nice properties. And now what you can, here's the question. Does such a model exist? And the answer is yes. And there's actually multiple of those infrastructures that, virtual infrastructures. And I'm going to talk about one. This slide is about GINI, okay? GINI stands for Global Environment for Network and Innovations. This is widely deployed in the US. There are similar infrastructures in Europe and in Asia, especially in Japan. But what you can do, right, is very simple. These are all the resources in the network, okay? And so you can see here that you have one host, another host. So basically what you have a GINI aggregator, so it can be a site that hosts GINI resources, okay? And so you can see that there are multiple of these big boxes. And within this GINI aggregator, you may have multiple hosts, right? So a site will probably have 10, 20, 50 hosts that are allocated for GINI purposes. And these are interconnected over the internet, right? And now what you can do as a researcher, and we do that, some of our research is actually implemented on GINI itself. What you can do is you can say, look, I'm going to run an experiment. Okay, and so what I have is I have this new software protocol that I want to test. And so you can go to the GINI and ask for, okay, a specific topology. So you can get a piece of this host, a piece of that host, and so on. Okay, that's called a sliver. Okay, and you can also get links between them. You install the software into that host, and then you are free to run your new protocol, your new software, and test it. And you can make this as small or as large an experiment as you wish. And the nice thing, the way that GINI is structured, of course, is that it provides isolation. So if your software is faulty, right? Obviously, something's going to go wrong with your experiment, but it will not affect another researcher who is also using slices of the resources inside the network. Okay? I'm sorry? What do you mean by cloud architecture? So cloud in the sense that you can use resources throughout the US, yes. Mm-hmm. Yes. Yes. Mm-hmm. Mm-hmm. Right. Yes, yes. Mm-hmm. Right. Mm-hmm. Right. Yeah. So it's in a sense it's similar with that, right? But the point here is that this is a internet-wide. Right, so it's not provider specific, for instance, right? Because in the cloud you have the Amazon cloud and you have the Google clouds, and they will not talk to each other. This is an open architecture that you can basically deploy just like the airline industry. Anyone can use the service of the internet. Yes. I'm sorry? Right. Yes. Right. So and I completely agree. So my point is that this is more about networking, which is not about the software services, right? So it's a bit more general because it kind of encompasses the software model. So whatever, the cloud as a service can be actually put on top of this, right? Okay, so, all right. And then finally, I'm going to take a few minutes and talk about software-defined networking because obviously it's an area of research that has basically exploded in the last 5 years or so. But more importantly, we have a proposal that is related to that, and I'm going to just talk a little bit about that. So, just a bit about the context. Typically, networking devices have been proprietary, right? So, you buy your equipment from Cisco or you buy them from Juniper, and typically the two will not interoperate, although they run the same protocols, open source but they basically make some proprietary changes to the protocol so to ensure that their equipment work better with each other than with their competitor. Okay, so there's a lot of reasons for that. And the other important issue here has been that most of these devices are hardware centric. Okay, and as one of my students, so I teach this data structure class, and I have one of these students who was taking this class last semester, and he told me, he came to see me. He's a local student, although he's taking distance education. He's local to the RTP area. He came to see me and he said, I did my undergraduate in electrical engineering. Is there an electrical engineer in the room? So he said, but that was a big mistake. I realized that all my friends who studied computer science, now they can, do their own startups and have an idea. They implemented the software. We hardware engineers, we can't do that. We have, we have to have resources, build the ASICs and all that. So unless you're working for a big company, he was actually working for Cisco. You can't really put your ideas into practice. So he said, I'm coming back to school and I'm taking all computer science courses because I want to, be good in software. All right, so there's a reason they are hardware centric, right? Because remember what I said is the most important thing in the internet today is to make packet forwarding as efficient as possible, okay, and keep up with the growth in network capacity. But obviously, because you are doing hardware, you are limited in how you can introduce innovation into your network. Okay, so if you look at the way that it works today, you take boxes from Cisco, as I said, from Juniper and so on. They have custom hardware, they have their custom OS, okay, and then you have features, and the features could be, Dijkstra's algorithm or OSPF and so on that work with together and do this. Now, it's okay. So you have billions of gates here, million lines of source codes, and so making any changes to this, right? If you have a new idea, you want to make a change, it's very problematic. Okay, it may take months and hundreds of man-hours to actually get it done. This is very similar to the way the technology used to work a few years ago, okay? So what you had is this vertically integrated industry, that mainframe industry, okay? Vertically integrated. If you want to have a computer, you have to go to Cray or you have to go to IBM and buy the computer, okay? And if you wanted to make any changes, you had to work with IBM to make the changes that you wanted, okay? What happened? What happened is that model has broken down completely, okay? And now what you have is microprocessors with open interfaces. Now you can build multiple different operating systems on top of this the same microprocessor. And then these operating systems also have open interfaces, which now you can have application providers or application writers, basically software writers. And so the Apple model has the Apple Store has maybe almost 1 million applications or more, right? Sorry? So that's the idea then. This is kind of the model to go with the network devices. Get away from these big routers that you can see, big routers and switches that you can see here, which is again vertically integrated, and then go to chips that are switching devices with open interfaces, that you have different operating systems or control planes, and then you can have features that go on top of that. And the idea there is that you basically have, so let me go this. So if you look at how the Ethernet switch works today, basically there are two planes, right? So there's a data plane and the control plane. The data plane just handles the packet processing. And then the control plane is the management interface that controls and configures the device. Okay, now both of these are integrated inside the switch. So if you buy an Ethernet switch from a manufacturer, it will have both the data path and the control path, and these are vendor specific, okay? And so what the idea here is that to completely take the control plane away from the switch, so completely separate the data plane from the control plane. The way that you do that is by moving the control plane into here, this red box over here, which is the network operating system, and the network operating system is not distributed, it's centralized. So what you leave at each switch is just the packets, it's just the data path and the packet forwarding, and then you just take the control away and put it in a central switch. And so this is the way that it works. So this is the control plane here, okay? That's the network operating system. The data plane is down here. And data plane is very simple. Remember, it only does forwarding. So it can be simplified significantly. And so the network operating system runs on controllers. The controllers are kind of centralized. They're separate from the switching devices. And you use a kind of forwarding abstraction to get state information and then configure the devices, and I'm going to get into that. So now you go from this situation where you have custom hardware, custom OS, and then things like routing protocols inside each switch, okay? And what you get to is very simple packet forwarding engines. You have the control plane over here, and now you can have the traditional routing protocols, and if you want a new one, you can just implement a new one, okay? If you were to implement one over here, it will be a pain. Why? Because this runs at each and every router inside the network, and so you can't just go and implement it because it may create chaos if there is a small bug and so on that may create a chaos, right? It's very difficult to integrate it in a distributed manner. Here, it's sitting on top of the controller, and so you can very easily just go in and plug it in, and the controller will take care of the rest. And I'll show you how this can be done in a moment. So this is basically how, so OpenFlow is just one standard way of communicating between the network operating system and the Ethernet switch. And this is the OpenFlow controller, but what I'm going to do is just show you some examples, right? So basically what you do is the controller will talk to the switches and tell them what to do, okay? And the way they do that is by using these headers, where you have a header and data. So the header comes in of the data, the packet comes in, has data in a header, and so basically what the packet switch does is just a matching operation, okay? And so you can do things like this. You basically have a table over here that tells the switch what to do. And let me give you some examples. So you have things like a rule, an action, and statistics. Okay, and the rules, the action can be forward the packets, encapsulate and forward it, send it to processing pipeline, modify fields, and any other extensions that you add. And so you could do things like this. If you want to just do switching, you say match the destination MAC, and if it matches, then send it to port 6. That's typical switching. You can do flow switching, where you don't match just the destination address, you match a whole bunch of fields that define a flow, and then you tell it, if you match all of these, send it to port 6. Okay, so that's flow switching. You can do firewall, which says if it's port 22, drop it. Okay, that's a firewall action. You can do routing that matches the IP destination address. You can do VLAN switching, where it just matches the VLAN ID and then sends it to whatever ports they need to go. And so basically the point is the following. The controller is sitting over here, okay? These are very simple devices, and you can come in, Alice can come in and say, look, I want to define this new operation that has these new rules. So it tells the controller, these are the new rules. The controller just downloads this to every device, and now Alice's protocol is operational. Very simple, just automatically, okay? Very small change, as opposed to going throughout the network and making changes to each and every, the software at each and every switch. And there are multiple interesting things here. You can have centralized control when you have a single controller. You can have distributed control, where you have more than one controller, so you can basically, if you have a very large network, you can break it up into smaller clusters. Each cluster controlled by a different controller, and then the controllers have to talk to each other. You can do things like flow-based forwarding or aggregated, so flow-based for a small LAN. You can do flow-based, so you can identify, you can say, well, the vice dean's flow get higher priority, right? And then professors' flows get higher priority than student flows, okay? So then you can do that. But of course, if you go to a wide area network, that is not scalable, so you will have to have some kind of aggregation, and you will say, well, all the flows from KAU are getting this kind of priority inside the network, and so on. It can be reactive or proactive, and you can do things like load balancing. Remember, one of the things that switches do is they collect statistics. So for instance, in a data center, this application would be very, in fact, Google has moved to an SDN-based network, and there are papers from Google that describe exactly how they have done that. But load balancing would be a very nice application where you decide which switch is going to process the next packet or the next service request, and so each switch will collect statistics. The controller will take these statistics, will run its load balancing software, so the load balancing software is centralized over here, and then downloads new rules that tell the various switches exactly what to do. And then the other thing that SDN is also very important for virtualization. The reason is virtualization is just another module that can be sitting on top of the controller. And so if you want to say, okay, here's my network and I want to get resources from and build a virtual network, you can describe that in the virtualization layer here and have the network OS operated. So this is the, let's say, this is the view of the network, but at the virtualization layer, you may break it down into things like this, okay? You can customize it as you want. So, and that's kind of ties the SDN work with the virtualization, as I said, okay? So that completes my discussion, and I'll be happy to take any questions that you may have. Yes? I'm sorry?
It's a part of SDN, I think.
Right. So SDN. So the way that I look at it is that network virtualization can be easily implemented using SDN.
Any question at the girls section? is no question.
Yes.
Okay, thank you very much.
Moving the control from the switch to the software, what is the implication of this on the performance of the system? Because it's known that implementing things using hardware, it's faster than implementing things using software.
Right. And so the forwarding actions are all implemented in hardware. That does not change. Okay, so this is the this is the OpenFlow client that is sitting on each of these machines. Okay, so so this is an OpenFlow client. This is a switching device which is connected to the various PCs. Okay, so this is the switch. So the only thing that happens in software is that you are. So let's say you want to do a routing algorithm, right? A new routing algorithm. So you're going to run the routing algorithm offline, or you can actually be running it online all the time and make changes. That is fine as well. And then what you do is you basically, so the routing algorithm will determine things like, you know, if a flow comes in on port 1 of this switch has to go out on port 2 of that switch. Okay. And so the only thing that is done in software is this running of the application, and then you download, you determine what the rules are, the forwarding actions or the other rules, and then you download these into the table. Now, the actual forwarding will be done by this machine, and it will be done in hardware. So as soon as you implement, as soon as you actually put in these flows, sorry, these rows in the table that determine what to do with this flow, the forwarding itself will be in hardware. Okay? What it does, it simplifies the setting up of these tables, which otherwise would have to be done in a distributed manner. So in other words, you're going to have those routers which exchange information, find the topology, run the diagnosis algorithm, then set their own forwarding tables, right? That complexity is completely removed. The router does not run a routing protocol anymore. The routing protocol is sitting over here. You still have the same information as the routing protocol, except that rather than the routers talking to each other so that each one of them has an exact copy of the topology to run the XS algorithm, they just convey that information to the controller. So now the controller has the complete topology. They can run the algorithm and download the forwarding tables. Now you can do much more sophisticated things, because instead of Dijkstra's, you can run a constrained path algorithm. So if you want to find a path that has this much bandwidth, you can do that. You can do that in a distributed way, right? Yes.
Okay. I need to ask you about some introduction about the previous of the old of computer science terminology. You can remember that we have before the type of the computer we have analog, digital, and then hybrid. This is the history of the computer we have. Then we go to look at the mainframe, mini computer, and the PC, and then we have laptop and so on. And then we go to look at the computer networks. We have the different types of the network. Mention about network topology. We have a star, mesh, and so on. And then when we go to look at local area network, we have wide area network, or LAN, WAN, and MAN. And then we go to look at the different series of such one. When I go to look at the data, we have centralized data and it's distributive data. And now we have at the last decade, now we need to look at this umbrella. Can you look at what is the category of you mentioned about it? We need to look at the terminology. What is the biggest terminology for this series now.
The biggest terminology for, I'm sorry?
I need to look at, to look at the naming of the series now.
The series?
Series or the science of such you have.
I'm not sure I understand.
Or the architecture, or the structure, or the layer, or series. Like such hybrid, digital, or man, WAN, LAN. What's the name of?
He wants to categorize
this particular area? Okay. I'm not sure that there is a name for that, because I mean, I talked about three different things, right? I talked about network architecture, and by network architecture, I mean the way that the network itself is constructed, okay? And then I talked about virtualization, which kind of allows you to have multiple architectures running onto same infrastructure. And then I talked about SDN, which is a way that you program the infrastructure so that you can get the virtual networks. And so these are all related, but I'm not sure that at least not to my knowledge, I don't think there is kind of an umbrella name that includes all of these types of research. So here's the interesting thing about networking research, which I mentioned a little bit at the very beginning. You can have an idea, and you can let's compare it to physics, right? If you come up with an idea about physics, about a new theory, right? The very first thing that's going to happen is that everyone's going to question you, right? It's going to say, okay, well, it's very difficult. So, I mean, there's a mindset, okay, you believe string theory, or you believe this A or B theory, and so on. And anything that is outside this mindset is typically challenged, okay? In network, now, to prove your new theory, you have to conduct, experiments at CERN, for instance, right? If you don't do that, and if you don't have access to CERN, it's impossible to prove your new theory. Networking is very different, and this is why, in fact, a person can make a difference while sitting on a computer and having just a high-speed internet connection. It's very different, because if you have an idea, you have all these platforms in which you can implement, experiment, and showcase that your idea works well. There's a very recent example of that. I don't know how many of you have heard about this 18-year-old boy who had a service developed for mobile devices and he was bought by Yahoo for about $30 million. So at 18 years old, what was his service? His service was that he was taking the full text news articles, right, as they come out every morning or throughout the day, and he was summarizing them and formatting them in a way that they can be easily read on a mobile phone, right? Yes. So Yahoo found this very valuable. I mean, this is an 18-year-old boy in UK, right? And they found it very valuable. They bought his company for $30 million, right? You can make that. I don't think you can categorize the networking research as A, B, or C, because people can come up with new ideas, implement them, and make an impact. As I said, you don't have to be in Silicon Valley. I mean, any one of you, if you have a good idea, you have good internet connection here, you have the infrastructure, all you need to do is implement it and demonstrate that it works, okay? Demonstrate the value. So that's the interesting thing about this. So I don't think that I can categorize networking research, because I talked about 3 different directions. There's probably a million others, okay? I can't talk about everything here, obviously. There's lots of different things that are going on, and this is why I think it's a very exciting time for for networking. So if you think about it, in the 80s, it was ATM research. In the 90s, it was internet web, right? In the 2000s, it was mobile, okay? Now, you have data center networks, you have Internet of Things, you have smart grids, you have energy efficiency, you have our cloud. You know, there's so many things that are going on. It has basically exploded, okay? And I think this is a nice thing. It gives you opportunities, okay? As a student, if you study networking, it's gonna be valuable for the next 30 or 40 years, which you can't say for many other disciplines. Okay, and so I don't think I can kind of categorize them into silos. Yes.
So, do you expect some benefits on the memoryless devices like mobile using this technology in the future?
Yes, of course. What do you mean by memoryless?
I mean, my mobile can be considered memoryless, which cannot be compared like a desktop machine.
It's not memoryless. This has 64 gigabytes.
No, it's not enough to put my database on it and to do processing on it.
Well, just wait for 5 years.
Yes,
Okay.
the question. Still, it is memoryless.
Right. So, I mean, no, I actually don't think that you need to do the processing on your, I mean, I don't think anyone actually does their processing on their desktop anymore, right? I mean, you do your processing in the data center. That's I mean, you have a Google document. You know, whenever we want to share information, we don't exchange documents. We just put a Google document out there. Google does the processing for us. We just, you know, you know, that's where the technology is going, I think. And so any of these areas of research will certainly benefit, you know, mobile phones, smartphones, and the way that we access the internet. That's for sure.
Any question? Thank you, Professor George.
Thank you.